It's about 8:30 in the morning on Tuesday, October 17th, 2023. It was a chilly night. It got down a little bit below 40, I think, if not just down to 40. Right now it's about 43, 45 degrees. It's warming up quick. The sun sure makes things warm. And the puppies are okay. I think I took a video of them. I'll probably share it. They were all huddled together. They're warm. And Mama was with them, of course, probably during the coldest parts of the night. Cows are okay, of course. Cows have a thick leather coat they like to wear with them all the time. And that leather coat has fur on the outside, so it's a nice fur leather coat. Not to mention the blubber, the fat that they have underneath that coat. The grass here is pretty good. This is the last cell of the third section. I have to make a decision whether to keep rotating or to push these guys into the back 20 for a few days. So I'm going to go over there and look, see what I can see. I'll look with you. I'll bring you along for the ride. I have not looked in the southern pasture. I have not made a decision. Because the first three sections were so good, I'm thinking of just keep rotating. But I need to get a good sample of what it looks like back there. So here we go. Looks like the cows found a pretty good spot to graze. This area here is pretty nice. The grass isn't as tall as it looks like in all the areas, but it's tall enough and they should be fed. They should have plenty of grass. All right, let's cross into the southern section. So far, it looks just like the last part of that northern section. Nothing to write home about. Oh, I'm seeing a lot of brown grass. Not too inspired right now. I'm actually a little bit disappointed. Quite a bit disappointed, actually. I see places where the cows took a bite of the grass, but I don't see that it's recovered. And that's concerning to me. I don't see new grass. I do see a little bit of new grass, actually. Not very much. We had rain, I want to say on October 5th or 4th, a good amount of rain. Something like 2.5 inches all told. So I thought maybe that would give the southern half of the field a big boost, because that's as we left the southern half of the field. But in reality, it only gave them like a week and a half of recovery instead of the full 3 weeks. So this area here, I was here 3 weeks ago, but 3 weeks ago it was dry. We were in severe drought, D2. When we did get rain, it's just a little bit of rain. Yeah, this is not looking very good. Yeah, I'm not impressed. Let's go take a look at the next section. There's lots of dew this morning, which is making my pants wet because the goat weed here is almost up to my waist. Now, there's some decent grass here. It's getting better. Yeah, I see lots of pointy tips now. Kind of show you what I'm looking at. I'm starting to see pointy tips, which is what I want to see before I declare the field recovered. There, that's a, I don't know if you guys can see that. That's a bundle of grass. I can tell the cows nibbled at that. And then there's a couple pointy tips coming out of it. Not too encouraging though. All right, now I'm in the fifth section. It's impossible for me to look at the whole section. Yeah, this area is pretty dry. I'm not seeing much grass at all. See that? This area is not good at all. Oh man. I guess I do have to go in the back 20 for at least a few days. But I can't hold them back there forever. Not without overgrazing the back 20. All right, I saw some, ooh, look at this. There's some pointy tips. We do have some pointy tips, it's not very much. The goat weed here is up to my knees. Now it's up to my thighs again. I've seen a lot of dead grass, not a lot of green grass. It's getting a little better, but that's not saying much. Yeah, there's barely any green grass at all. Oh, yeah. If I do move them to the southern pasture, I'm gonna hay. So that's what I'm gonna do. Okay, this is a little better. I saw some signs of hope. I'll kind of show you what I'm looking at. There's something down there growing. Not very much and not very strong. It's getting a little greener. There we go, now it's green again. All right, just not a lot of growth. And if the cows were able to nibble at it, I wouldn't want them to. It would kill the grass. Okay, this is the 6th section. Crossing the 6th section right now. This was not a good section either. Oh, there's a little bit of green. Yet again, there's grass that they nibbled on. That is just now starting to recover. So this is 3 weeks ago. Or 2.5 weeks ago that they were here. 3 weeks ago. 3 weeks ago, less than a day, I saw my first grasshopper in a long time. The grasshoppers are over here. The goat weed is getting shorter now. Yeah, the grass just needs more time. There's pointy tips there, but it's so short. It's like it's mocking me. It's like it's telling me that even if I do recover, there's not going to be much there. Yeah, I think I'm going to roll out some hay. Just to give them something to eat. The issue is that even if I roll out the hay, they're still going to nibble at the grass, and that's not what I want. So I have to find a piece of my field. Well, this is encouraging. That looks a little encouraging, doesn't it? I have to find a piece of my field that I'm willing to sacrifice and kind of box them up there and then feed them so the rest of the pasture can recover and grow. Ooh, this is starting to get a little nice. This is what I want it to look like after I've grazed. Let me just kind of give you a side picture of that. That's what I want it to look like right after they leave. Even then it's a little too short, but there's taller grass here that they left behind. Yeah. Here it's kind of spread out and flat. So yeah, I'm disappointed. I'm not surprised, I'm just disappointed. One of the possibilities that I was anticipating is likely, not just possible but probable, has come to reality. So if this were the poorest part of these sections, I would probably do a rotation, continue the rotation through here. But since this is one of the better parts of the sections, I'm going to say no. All right, so I got to figure out where am I going to put the cows while I feed them. What part of my pasture am I going to sacrifice? Do I sacrifice a part of the pasture that's not doing well? The idea is that there'll be more manure down there, more urine, and also rolling out the hay in that area should provide that area a head start. One of the things I read in Greg Judy's books, though, is that you roll out the hay on your best grass, make it even stronger. You get better results that way. If it were winter and the grass wasn't growing at all, I probably would do that. But since it is still growing season, I don't think I'm going to do that. Shifting gears, I read an article in the American Thinker about this guy. He works at the gas laboratory. What that is back in the 1830s, the people who were selling propane realized that although their instruments were accurate, when they measured the gas at high pressure versus low pressure, they got different readings on how much they were measuring. And so they built a laboratory to measure and experiment so they could try to get those two numbers to reconcile or understand what's going on. They discovered fairly early on that the ideal gas law doesn't work. They also discovered that the professors who claim to know how temperature, pressure, and volume and the number of particles, those people who claimed to know what they were doing didn't know what they were doing. And I would agree, in the 1830s, I wouldn't trust a physicist either to tell me what temperature it is. Modern thermal physics and statistical dynamics, which have pretty much been joined together, those two theories grew out of experience that people had noticing that the theories of the day weren't working, right? They just were inaccurate. Rather than adapt the theories, they came up with new theories about what's really going on. And these theories, sometimes they call them the modified theory or something like that. But these theories are much better at matching the experimental results. Okay, the thing is those theories really didn't exist in the 1830s. So it's because of the work of people like at the gas lab that we discovered that what we thought was the nature of reality wasn't in fact the nature of reality. And we were able to come up with new explanations for what's going on. Okay, modern thermal physics. The equation that for the ideal gas law is PV equals nRT, right? PV is the pressure and the volume, multiply them together. N is the number of particles, usually measured in number of moles. And R is some constant just to make everything match. And then T is a temperature, right? I was thinking about this. A lot of equations in physics are convenient because they are made to be convenient. And in this case, our understanding of thermal physics and statistical mechanics says that the quantity we should be measuring is the inverse temperature, right? And that way we get rid of the whole problem of absolute zero. Absolute zero would not be possible because that would be infinite temperature and infinite inverse temperature, right? And so as you got closer and closer to what we measure as absolute zero, the quantity that we would use for temperature would be the inverse temperature, blah, blah, blah. Okay, so we could have used inverse temperature, right? We just didn't know when we were doing PV equals nRT that the temperature was supposed to be inverted, right? And so all of the statistical mechanical equations that relate temperature to the motion of the particles, it's an inverse relationship, right? It just makes more sense to make it inverse. Okay, one of the things in the article that he says is temperature is kinetic energy. This is false. This is not true. If you imagine that the kinetic energy of the particle somehow stores the temperature or indicates the temperature, you're going to get a lot of stuff wrong. The reason why it's wrong is because of entropy. Okay, what entropy is we discovered when we were building our engines, our steam engines, that some of the energy was inside. That's the N of entropy. Some of the energy was inside and we couldn't access it, we couldn't get it out. And it was weird because the energy that we could use for useful work, or that came from useful work, right? If we increase the pressure or decrease the volume or whatever, that energy was lost forever, right? Couldn't be recovered, okay? And so entropy was a concept, and a lot of experiments, you can uncover the value, the quantity of entropy through experimentation. It's not that hard, right? The statistical mechanical interpretation of what entropy is and what temperature is, those things are very closely related to each other. And the easiest way to understand it, if I were to explain it to somebody who doesn't really understand much about math, is I would say that imagine if you have a cup of water, right, and another cup of water, right, 2 cups of water, they're separate. There's like these chessboards, these really huge chessboards, right? And on that chessboard, you can put like pieces, like tokens or checkers, right? Those checker pieces represents the packets of energy, the units of energy. Okay, you don't even need to understand quantum mechanics to get this. Okay, so if one cup of water has more units of energy than the other cup of water, that means there are more pieces on the checkerboard than the other. That's all it means, right? The question is, what happens when the 2 checkerboards come in contact and the pieces are able to move between the boards, right? Now, the first thing you have to understand is that nobody really knows what's going on inside. We can't predict the motion. All we can say is that something is more likely than something else, right? So, for instance, it's more likely that the checker pieces will be spread more or less evenly across the board, right? So half of them will be on the north side and half of them will be on the south side, right? Then it's much more likely than it is that all the checker pieces are on one side of the board, right? And you can probably try this out for yourself. Take a random number generator from the internet and, take 10 checker pieces and roll a random number between 1 and 64 and count out that many squares and put that piece on the board, right? Do that multiple times and you'll see, in fact, that most of the time the checker pieces are spread more or less evenly across the board, right? And so that's why we talk about what's likely and not what's possible. It certainly is possible that all the checker pieces are on the same square, right? It certainly is possible that all the checker pieces are on one side of the board, and so on and so forth, right? Okay, but it's not likely, right? The number of checker pieces and the size of the boards for something that we're used to in everyday life, like, a cup of water at room temperature, right? Or just the air around us, like a certain volume of air. The numbers are so huge, so ridiculously huge, that I have nothing that I can compare those numbers with, right? So they kind of stand as a league on their own as very, very huge numbers. I'll try to give you an understanding of how huge these numbers are. So let's say I had the number 1 million, okay? And I add 1 to that 1 million. Now we get 1,000,001, right? We can count 1,000,001. But the thing is like all of the instruments we use to measure things in millions, there's no way we're going to be able to tell if 1 is missing or if 1 is extra, right? Okay. So if you have 1,000,000 candy bars and somebody snuck 1 out and ate it, how are you going to know, right? Unless you sit there and count all million, it's going to take forever, right? So the numbers 1,000,001 they just don't compare to each other. And the way that they don't compare is adding 1 to 1,000,000 really doesn't change the 1,000,000. Okay? That's the way they don't compare. So we say 1,000,000 is much larger than 1. And the implication is that when we add 1 to 1,000,000, it's like not doing anything at all, right? Especially in terms of physics, when all we care about is like 3 or 4 significant figures. You know, unless you're adding 1 a million times, it doesn't matter, right? So that's a large number, 1 million. Okay, now imagine a number so large that multiplying it doesn't change it. So let's take a number, let's just call it a goobly-goo, right? And I multiply a goobly-goo by 7. And this new number is basically a goobly-goo. There's really not much different between the first goobly-goo and the second goobly-goo that's been multiplied by 7. That's how large these numbers are. And I know that it's impossible for you to really grasp the size of those numbers unless you understand exponents and what I'm talking about here. So the goobly-goo, the number that's so large, is basically something raised to the power of 1 million. And when you multiply by 7 or 10 or whatever, now it's the same number, but it's raised to the power of 1,000,001, right? So it really doesn't make a difference. That number is basically the same. So those are the numbers that we're dealing with when we're doing, statistical mechanics. Like that's how many checker pieces are on the board. That's how many cells are on the board, right? What we find is that when we start dealing with those large numbers, and we have to do some funky things with math in order to solve these math equations and figure out what's going on, really funky things, right? Things that would, cause your hair to fall out if you really understood what we were doing, right? But because of the nature of these numbers, it's perfectly fine doing these things. We can say that not only is it likely that half the checker pieces will be on the top and half the checker pieces will be on the bottom, we can say that you will never observe any other situation, right? You will never observe any other situation. You can watch it for the lifetime of the universe. You can watch 1 billion experiments for the lifetime of the universe. You can watch an experiment for every particle in the universe for the lifetime of the universe. And you will never, ever, ever once see the particles arrange themselves such that there's not the same number on the north and on the south, right? So the implications of this is when you bring those 2 checkerboards together, these 2 massive checkerboards with a huge number of particles on them, and you allow the particles to randomly move between the boards, and this is what's happening when 2 things come in thermal contact with each other, then the most likely result is that the number of energy packets on one side will equal the number of energy packets on the other side. That's temperature. That's what's going on. Now, entropy describes the number of ways that you can arrange the energy packets. Okay, so entropy are these huge numbers, right? Okay, because if I had like one piece on a checkerboard of 64 squares, there's 64 ways I can arrange that energy piece. If I had 2 pieces, that's 64 squared. If I had 100 pieces, that's 64 to the 100, right? Okay, so there's truly huge numbers, right? And so entropy is so large, in fact, that we don't even look at the number, we look at the log of the number. So we take the log and we just look at the exponent. That's the number that we care about, right? That's the number that we worry about. So that's entropy. Entropy tells you how many ways you can arrange the energy packets on the board, okay? And the rule that we've discovered is that nature operates in such a way that when you allow these random processes to occur, that they will arrange themselves in such a way that the number of ways to arrange them is maximized, okay? Does that make sense? So if we bring the 2 checkerboards together, the energy packets will arrange themselves in such a way that the maximum number of arrangements is achieved, right? Entropy maximizes over time. Okay, entropy is just the count of the ways that you can arrange those things. That's all it is. And entropy is maximized. That's when we do random processes, that's what happens, okay? It doesn't matter how the random processes happen. It doesn't matter what mechanism the energy packets, what form they take. It doesn't matter what the checkerboards are, right? It doesn't matter. In the end, energy arranges itself randomly. If it arranges itself randomly, it will arrange itself in the way that maximizes entropy, okay? Now temperature measures some quantity about the object, and that quantity is not the number of energy packets inside, although it is related, okay? It is not the number of ways you can arrange those energy packets, although it is related, right? So temperature measures how hungry, or rather how willing the board is to share pieces, the energy packets, with another board, right? If it is arranged such that if you add a piece to the checkerboard, you get a huge new number of ways to arrange that energy, then that system is hungry. It wants more energy packets. If another system is set up such that if you add more energy packets, it really doesn't do much. It really doesn't increase the entropy that much. Then the temperature is low. It doesn't want new energy packets. It would prefer if those energy packets went somewhere else. And I say prefer, not like they actually have a choice, but randomness says so. Randomness says that the energy packets will move a certain way. The energy packets will move from the places where there is a low number of ways to arrange them to the places where there is a high number of ways to arrange them. Got it? Okay, good. Now, what is this energy board? What is this board? The board is not the number of particles, although it's related. Okay? The board, the number of cells on the board are the number of ways you can stow those energy particles in the system. Each particle has multiple cells. If you think of a point particle that can't rotate, then you can think each particle has basically three cells. One cell for motion front and back, another cell for motion left and right, another cell for motion up and down, okay? Some particles are built in the shape of a cylinder, like hydrogen, oxygen, nitrogen, everything like that, right? Those particles, because they're a cylinder, let me put my finger out here, they can also rotate this way, and they can rotate this way. They cannot rotate this way. That doesn't mean anything, okay? So they have five ways to arrange the energy packets per particle, okay? So question, if you had a monatomic gas, like helium, okay? Helium comes in single atoms, and it had a certain number of energy packets. And you had a diatomic gas, like hydrogen, and it can arrange itself in even more ways. Which way would the energy flow? Would it flow from the helium to the hydrogen? The answer is yes. If the helium and the hydrogen have the same amount of energy, then the energy will flow from the helium to the hydrogen, because it doesn't matter how much energy they have, it matters how many ways they can arrange it. Whew! Okay, last little bit. Some particles have 3 or more atoms, and they can rotate one way, they can rotate the other way, and they can rotate a third way. So they can get 6 ways to arrange that energy packet. Some particles also have modes of oscillation. So the 2 particles can go like this. They can wobble together like a spring, right? So you got to add all that up, okay? Ultimately, we measure the number of ways energy can be stored in a particle using experiment, right? And, some particles are better than others. If at very low energies, at very low temperatures, some of the states are inaccessible. You just can't get enough energy to cause the particle to move in that way, okay? At very high energies, new ways of storing the energy are opened up, right? You can imagine at like thermonuclear temperatures, like inside a nuclear bomb, you can start seeing oscillations, not just of the electrons around the proton in the middle there, the nucleus, but you can also see oscillations of the nucleus itself, right? So we're talking ridiculous levels of energy, okay? So that's kind of the story there. Okay, now, why am I telling you this? Because they misrepresented energy. They said, oh, it's just the amount of, kinetic energy. They said temperature is kinetic energy, it's one and the same. No, they're not, right? It's very important. The shape of the molecule plays a huge role in how temperature flows, right? Okay, long story short, why global warming is bunk and why it's stupid. Specifically, the greenhouse effect caused by carbon dioxide. Carbon dioxide is 1 carbon, I'll just use my finger for the carbon, and 2 oxygens, okay? Now, in water, the oxygen and the hydrogen are arranged like bunny ears, so they can rotate in all kinds of different ways. In carbon dioxide, it's arranged in a line. Just like nitrogen, just like oxygen, just like everything else that's diatomic. It behaves almost exactly like nitrogen and oxygen, okay? The differences are minute, especially at temperatures that we're familiar with, okay? All that to say that carbon dioxide is not special, okay? I didn't tell you about how energy is transferred. It doesn't matter. I didn't tell you about what form the energy takes. It doesn't matter, okay? All that matters is the energy It can be distributed among different systems, among the particles of that system in different ways. And the number of ways you arrange that energy determines how the temperature behaves. Period. That's it. End of story. Okay. Lastly, the article on American Thinker does mention that experiment is king. You can have all the theories you want, but unless you can make an experiment showing it, it doesn't matter. Okay. All you're doing is you're blowing smoke. Okay. There is no experiment that demonstrates the so-called greenhouse effect of carbon dioxide. There is no experiment that measures the greenhouse effect of carbon dioxide. Those numbers are made up. Somebody looked at a piece of paper and scribbled something down and said, that's the number. Okay? That's all it is. Okay? For lack of a better word, it's just an idea. It's just a theory. It's not even a logical theory. It's not based on thermodynamics or anything like that. It's based on nonsense and silliness. The silliness of the global warming greenhouse gas theory is so silly that I don't even know how to begin to debunk it. It's like childish. It doesn't even understand the first things about thermodynamics, right? It's retarded. It really is. It's like you took a kid with no understanding of how the world works. You stuck him in a room and he drew on the wall and you said, oh, this is the truth. There's nothing there, right? It doesn't make any sense. I can't even debunk it because there's no claims that it makes it can be debunked, right? That's the problem. There's no science behind it, right? It's like a scientist trying to argue with a Christian where the Christian says the world is flat because the Bible says so. And the scientist is like, well, maybe, there's some evidence for your claims besides the Bible. And they're like, no, all I need is the Bible. Well, how are you supposed to argue with that? How are you supposed to persuade someone like that? You can't, right? You can't. You need something scientific, something objective that you can both agree to, that you can measure. Well, in the case of the greenhouse effect, there's nothing you can measure. There's no experiment. It's just conjecture. And every time you try to pin them down and try to get them to write down their theory in a way that can be measured, in a way that can be attacked, they flibber flabber, go. I don't know what you're talking about. You're just making it confusing. Why don't you understand? Why are you so stupid? For asking simple questions. Anyway, that's where we're at. Sorry about the long video. It's really critical, I think, that people understand what temperature is and how it works. It's really critical that people understand that thermal physics and thermodynamics is one of the best understood areas of physics. And we know exactly what will happen to the atmosphere if we add a little more carbon dioxide or take some away. We know exactly. We can measure it. I can set up an experiment at home, and I can measure and show you the difference, the atmosphere, when we change carbon dioxide out. Okay? And the answer is nothing much. Maybe very, very slight cooling. Such slight cooling that you won't even notice it. You can't even measure it. Okay? Certainly, you won't even notice in the variation of a temperature of the day, right? We're talking fractions of a degree. Fractions of a degree, right? A very, very slight cooling effect, right? Nothing significant at all. Doesn't change anything, right? That's what we're talking about. All right, guys, you have a great day. Take care and bye-bye.